I know you're all excited about this future intelligent development into electronics, but we're still organic, okay? Yes. Yeah, that's mergence with the phone, yes, it's dangerous already. True. All right, so we continue with the panel discussion, our session 2, possibilities for non-terran life in the universe. And we have perfect introductory lecture today, didn't we? And so I take my seat here. And we had fantastic speakers yesterday, and we have fantastic panelist members today. So we'll start with the self-introduction of the panel. And I want to ask every panelist actually conclude the introduction of your research with a statement. What do you think life is? I'm sorry, I'm pasting everybody. What life is, okay? So such a simple question from your perspective as a researcher. What do you think? So you want to start? Or we start from the other end? Or
however you would like.
Sara, why don't you start?
Sure. So I'm Sara Walker. I'm an assistant professor at Arizona State University, and I work in the Beyond Center for Fundamental Concepts in Science and the School of Earth and Space Exploration. I'm trained in theoretical physics, but I mostly work on origins of life and trying to understand universal properties of life. And so a lot of that work is really focused on understanding information in biological systems and how information might be distinctive to living systems. And so most of my thinking about life is that really it is the next frontier in physics. We have inadequate physics to understand living processes right now. And if we did have a theory of life, it would be on the status of our theories of general relativity and quantum mechanics as far as its revolutionary power in transforming the way we think about reality, which I think is nicely resonant with what Martin was talking about earlier about this kind of new frontier. And there are a lot of things that are really fascinating about trying to get at that. I think a lot of work in complex systems has really been uncovering interesting properties of networks and information in biology that hasn't really transcended into how we look for life. And there's a lot of useful ways of thinking about looking for life that are not necessarily chemistry specific. And so I'm interested in exploring those topics. And so from that perspective, there end up being a lot of really interesting things. There was a lot of discussion yesterday about universal properties of life and how we might think about those. And they tend to be really focused on this level of thinking about life as chemistry. But if you think about life, we see life existing as a hierarchy on our planet. So we have individual cells, multicellular organisms, cities, societies. And if you start thinking about how life organizes across those scales and looking for universal properties across those scales in terms of how networks are organized and how information is actually structuring those systems, I think that opens a lot of possibilities for actually getting at universalities that aren't contingent on just the chemistry we have for life on Earth. So you asked a question though, so what I think life is. Oh, right, okay. So actually this is really funny because my research group, like once a semester, we have a what is life discussion and everybody's like definition of it is a moving target. But mine tends to be about, so I think there's a couple things about life that are really difficult. One is that we want to place a boundary around it, and it's not a process that has boundaries. So the short definition is it's a set of correlations in space and time that construct new possibilities as it unfolds. That's my definition.
Wonderful, thank you. So Clara?
Hi, I am Clara. I'm a quantum astrochemist at MIT, and my research focuses on figuring out what every possible biosignature gas might look like, primarily by simulating the molecular spectrum. And when I'm asked the question of what is life, I think the trick is to not focus so much on what life is or might be, but on what life must do. A lot of speakers touched on this before, so I won't go into much detail, but what we can say with some certainty is that on Earth, all life metabolizes and produces byproduct gases. And these gases are made up of literally thousands of small molecules. So alien life would be expected to also similarly produce thousands of molecules. And we may not know what alien life would look like, but it still has to make use of the same physics and the same chemistry that we have available to us. And there's a finite number of elements in the periodic table, and as such a finite number of molecules that life can assemble and then release into the atmosphere. So if the physics and the chemistry is limited, then so will the biology. But it is because of this this kind of limited but very vast number of possibilities for the biology of alien life, that I've decided to care about every possible molecule that could be contributing to an alien biosphere. And that's the motivation for my work, and until I die, probably, because it takes a really, really long time to really know one molecule. And so if we're going to know thousands of molecules really well, that'll take a really long time. I'll give you an example. The list of molecules that Sarah Seeger was mentioning yesterday is kind of the starting point for my work. And that's 15,000 molecules that we could be considering in a variety of alien biospheres. And for those 15,000 molecules, we know some spectral data for about 600 of them. And we only really know properly a few dozen of them. And one of those is phosphine, my favorite biosignature gas, but that's for another time. And I spent my entire PhD just simulating that one molecule. It took me 4 years to simulate 16.8 billion features, which together form the fingerprint, the spectral fingerprint for phosphine. That's one molecule, 4 years, one expensive supercomputer. So if I was going to tackle those remaining 15,000 molecules at this rate, it would take me 55,000 years. And JWST will be providing us with data definitely sooner than that. And by then, all of this data should be ready and tested and integrated into atmospheric models. Otherwise, we'll get all this amazing insight and, well, all this amazing data, but from which our insight will be limited. So that's what I focus on now. I quickly try to simulate these thousands of missing spectra by combining organic chemistry with computational tricks and quantum chemistry approximation. And that way, I'm hoping to reduce those 55,000 years to at least something that resembles my lifespan.
Well, we definitely need artificial intelligence help here.
Any help would be wonderful.
Yes. All right, thank you. Anders?
So I'm Anders Sandberg. I'm Senior Research Fellow at the Future of Humanity Institute at the Oxford Martin School at the University of Oxford. And I'm originally a lapsed computational neuroscientist. I did my PhD on building neural network models of memory. And I think the most useful thing from that is, of course, this ability to do models. So I ended up in the philosophy department, go figure, where we at the Future Humanity Institute, we try to think about the long-term prospects of humanity. And literally long-term, not 10 years or 50 years, but till the end, whatever that is. And both trying to apply the philosophical question, what would be a good future? And then the more practical question, so what can we do to get there? That means that a lot of our research is going to be about existential risk, because that seems to be quite clearly one of the top priorities. We don't want our civilization or our species to end badly. So the question is, of course, what we can do, what the risks are, how to analyze them, how to think well about these really uncertain topics, which means that a lot of our research is dealing with all sorts of doom and gloom of interesting kinds. But we also look at the positive side, emerging technologies and how they can help us and change us and indeed lead us perhaps towards a post-human future, as well as the philosophical question, is that a good idea? Now, the reason I ended up here, besides that I always wanted to actually go everywhere in the universe and figure it out and so on, that is because the Fermi paradox, or rather the Fermi question, seems to be one of the more glaring ways we can actually learn something very important about prospects for intelligent species. The fact that the sky is silent tells us something, and if that something has a bearing on the average lifetime of a civilization, then our institute is really keen to figure it out. So we have been involved in that. I was involved in setting up the UK SETI research network, where we're trying to network together people interested in that. But also some of my research deals with both how to build the kind of post-human futures. I've been working on the question of can we actually achieve brain emulations or artificial intelligence, as well as how big is the future? Normally when you talk about the end of the world, that's bad. And we want to avoid bad things. But we also want to go towards what is a good thing, a good future. So the question is, if we get our act together, how good could it be? How big could the future be? So that's my current big project, trying to actually understand how far can we go along different dimensions in space, in terms of how much matter we can mass, how much information we can gather and process, what can be understood, how much true value can be achieved. Now, getting back to that question, what is life? I think, unfortunately, I've been slightly infected by being in the philosophy department because I don't think there is an answer to it. I think it's a bit like asking what's personal identity, and I actually believe personal identity deep down doesn't exist. However, from a practical standpoint, obviously, I'm separate from you, and it would be very awkward to have conversations if we couldn't distinguish ourselves. So there is a kind of practical thing that where my skin ends, that's probably roughly the end of my identity. And similarly, I think life is something like that. There is no true universal category of life, but I think we're going to kind of know it when we see it, and we're going to find some awkward border cases where we might not be able to make up our minds. But I don't think deep down, no, there is nothing. But in practice, we're probably going to be used some of the definitions the more sensible members of this panel have.
Great. I would say, philosophically speaking, there is no answer to any question, isn't it?
Are you certain?
You can argue with any answer, I think. Yes. But let's be somewhere between science and philosophy so that we speculate on some answers. Thank you. And we're lucky to have two co-chairs of the session one here. Please, Chris.
I'm Chris McKay, NASA Ames. I was here yesterday. And I'm going to start with your life point. I would suggest not a definition, but a description of life is a system that undergoes Darwinian evolution. And right away, yes, a mule is alive. That's the common thing people throw out. And if we found a mule on Mars, that would be proof of Darwinian evolution on Mars. You don't need to find an organism that does reproduction, adaptation, and selection to understand that Darwinian evolution is what produced that organism. Even if the mule was dead, it would be evidence of life on Mars and Darwinian evolution on Mars. And that's been called the NASA definition. And since I'm at NASA, I have to subscribe to that definition. But I would submit it's not a definition, it's a description. As I said, I was here yesterday, which was unfortunate because it completely changed the focus of what I'm doing. So here's my new approach, and I'm going to blame several people in the audience for this shift in my perspective. Alfonso Davila and Steve Benner convinced me yesterday that finding a second genesis, another example of Darwinian evolution on a water world, and convincing ourselves that it was different from us is impossible. We just cannot identify a trait that is a variable trait that precedes the onset of Darwinian evolution. And so we'll never, and until we had a complete record of the steps from the origin of life to Luca, we'd never be able to figure out where any water-based like life would relate to us. Thank you, Alfonso and Steve, for destroying my view on that. It was also destroyed by discussions at lunch with Charles Offria, I think that's how your name was pronounced, who, running just sort of a thought experiment, we decided that in AI simulation, one could easily show that this was the case, that there are no features, variable features, that precede Darwinian evolution so that you can necessarily precede Darwinian evolution, so you can rule them out as being Darwinianly selected, and so their variability would indicate separate genesis. So much for that. So then Morgan Cable gave us the answer, go to Titan. Titan, we can find life that really is a second genesis. So now I'm hell-bent on Titan. Go Dragonfly, right? Because there we might find evidence of life that really is sufficiently different that we can call it weird, or they can call us weird. It's all relative, right? When you only have two examples, you don't know who's normal and who's weird. And that's where we can answer the question. And that's the question that I'm interested in. I'm not interested in finding life on other worlds. I'm interested in finding another example of a Darwinian system that is clearly independent and separate, because that would then address the Fermi paradox. That would then address our understanding of life in the universe. That would address X, a whole bunch of things, right? So I'm on Morgan's team on this. And then another big insight, I think, which came up at the panel, and I tried to deflect it from the conversation, was Avi's comment that why aren't you doing more lab work, right? We learned a lot about physics by doing lab work. Why don't you exobiologists do more lab work? And he's right. But most of the lab work we do is in water and water-based systems. But Stephen and Alfonso convinced us that that's pointless. So we should be focusing our lab work on Titan simulations, getting organic material, trying to make it grow, trying to get it to Darwinianize in liquid methane or ethane. So I got to leave early because we're going to start those experiments this afternoon. Thank you, Avi. So as a result, now of that meeting yesterday, my research agenda is completely different. So I can't imagine what will happen today.
Yeah, in this case, like Steve said, he believes that the life will be second life will be first found in the lab. So if we start doing those experiments, we will create life there, and then we'll search for something similar.
And we might as well do the experiments in liquid methane or ethane, because then we can check it with a natural system.
Exactly, yeah. All right, thank you. Penny?
Yeah, so I'm Penny Boston, and I'm the director of the NASA Astrobiology Institute, and I too was here all over the place yesterday. So I won't say much about that. I think that searching for a crisp definition of life is a fool's errand. We can spend our time much better than that. A description is maybe useful, where we all have different perspectives because we all come from different disciplinary traditions. My own personal little laundry list is insignificant, but let me just articulate a couple of the main things, and that is I really like boundary conditions, whether it's a membrane that we have here or some kind of magnetic creature that is living in a magnetic bottle. I don't care, as long as there is an inside and an outside so that there can be a net export of entropy, so to speak, increasing the interior order of the system. And then the other point is really that it has to be an evolving system. And when I think of biology, I think of it as the great spectacular example we have of the broader class of interesting systems, which are complex, multi-unit, and non-linearly interacting system. Life is the one example of that we really know in nature, but maybe there are others. So from my point of view, things like Charles is doing with the modeling systems within the computer is just as valid a way of looking at life in general. My own particular interest in this area of weird life, whatever that means, is how would we recognize life divorced from the chemistry? So the chemistry is very important, and we have spent a lot of time thinking about that. But I want to know what really produces a pattern in a biological system. And that pattern creation can be a pattern within the elements that are used. It can be a pattern within the molecules that are assembled. They don't have to be the same pattern. Or one thing that I think is really neglected, and that is the patterns that are created at a higher level by the interaction of organisms. So the patterns that we see preserved in the rock record, the ones that are the most distinctive, we take that pattern as a proxy for the fact that organisms have created it. We have faith that since we are made out of organic materials, that our precursor organisms were made out of organic materials. But in many cases, there's scant evidence of that. There's a complete replacement. So the ecological demands that any biological system has to drive it to work means that there are certain universal needs. And one is, in order to create lower entropy on the inside of whatever this creature might be, you have to have the capture of energy and its useful employment to rearrange things, and then the export of other materials. You need to arrange yourself in space so that you can actually capture those. So I think that we are not focusing as much on structure. We are hung up on, are we going to find cells or not? What about whole microbial mats? And I know there are people that certainly have looked at stromatolites and other examples, but I think that we are missing even higher scale patterns that organisms create, both chemically, physically, maybe intellectually. I don't know. So that's
all right.
That's
Thank
it.
You.
Yeah.
Thank you. Chris?
My name's Chris Chiba. I have a joint appointment at Princeton in the Department of Astrophysics and at the Woodrow Wilson School of Public and International Affairs. At the Wilson School, I spend most of my time on issues of nuclear and biological weapons, arms control, and nonproliferation. In astrobiology, my background has been in volatiles and organics in the outer solar system, especially in comets, and their possible interaction with the origin of life on Earth, and more recently, the chemistry and physics of Europa in particular, and the possible ecosystems on Europa. I wanted to make a few broad observations about the discussion yesterday, both the morning and afternoon, and the discussion this morning. Much of this discussion, I think, has examined almost a century-old discussion in the field of origins of life and exobiology, which is the extent to which you can extract from this highly contingent history of life on Earth general conclusions about life elsewhere. What can we say about life elsewhere, given how contingent life on Earth has been? And Lynn Rothschild addressed some of this explicitly in her remarks. And we had cautions. Dave Smith's talk about the clouds not being green was an example of a caution. But yes, the clouds on Earth aren't green, but you know what? They're very cold and they're subject to UV and they're not long-lived, so we shouldn't extrapolate from that to conclusions about clouds on Venus, as Dave Grinspoon argued. We had a discussion of the history of multicellularity on Earth and how that's tied to the rise of oxygen, because you can get so much more energy if you have O2 as your terminal oxygen receptor. But on Earth, that seems highly contingent, right? You have to sequester the organics to separate out large quantities of organics from the oxygen. There's a discussion about how all of this happened. Just to emphasize a contingency, one model is that you deposit a lot of these organics in alluvial fans. And that is then therefore related to the rise of continents, the creation of mountains, and so on. So the whole thing seems to be highly contingent. You go to a world like Europa, the very radiation environment at the surface, which makes it so difficult to operate on the surface, produces oxygen in the ice at the 1% level present in the ice at the surface. And if that ice exchanges with the ocean, if it exchanges with the ocean on less than 100 million year timescale, then given people's estimates, which I think are highly uncertain, but given the published estimates of the production of reductants at the bottom of the ocean, you can oxygenate that ocean at levels that are well above levels of oxygen in the Earth's oceans. So naively permissive of multicellular life. Now, the next step in that conversation, and there's a paper in 2007 by Kevin Hand and colleagues, but the next step in that conversation is to ask, okay, but if you actually had oxygen consumers there, how quickly would they be limited by the amount of oxygen supplied to that ocean? Steve Benner's talk yesterday made an effort to look at, if you assume that Darwinian evolution is a necessary component of life on Earth, what can we say that's generalizable, that we can feel confident in about the nature of the replicating molecules? And he made his argument for the negative monopole being an essential part of any such mechanism. And of course, this argument over contingency versus convergence just underlies the whole discussion of SETI and the evolution of intelligence on Earth. Is evolution of intelligence so contingent in our history that we shouldn't expect it to be common elsewhere? And that argument has literally gone on for a century, and it seems interminable. But I'd like to emphasize that I think we can chip away at it, but there's work that is not likely to get funded by the National Science Foundation that I would think any SETI project ought to consider funding. And let me give an example. This is not at all my work, so of course I'm on dangerous ground. It would seem to be interesting whether, right, so over time, the average intelligence on Earth, so to speak, has increased, but that doesn't mean there's some underlying driver to intelligence. That could be a random walk, right? If I execute a random walk away from this wall behind me, and at each step I'm as likely to go forward as backward, over time I will slowly move away from the wall. That doesn't mean there's a driver, it just means there's a wall behind me. A question regarding the evolution of intelligence on Earth is that, has there been some overall driver, or has it just been a random walk? There was a paper by Lori Marino and Dan McKay and Mark Ewan in 2004 that looked at that sort of question. They looked at the evolution of intelligence measured by brain-to-body ratios in toothed whales over the last 50 million years. And Dan McKay did the maximum likelihood modeling, and they looked at the question of whether you could explain the trends in intelligence among those different species as a result of a pure random walk or as a result of a random walk that had some weighting to it that was pushing towards, across species, pushing towards greater intelligence. And they found that a random walk seemed to explain that evolution perfectly well. That's a tiny little example. The NSF is not going to fund that work. It was funded by a small grant from the SETI Institute. But I think that some of these questions, instead of them being interminable, we could at least make some progress with. And I think that's an important objective, even though we have to be humble about what we infer from this or that little addition. Exactly. This contingency issue ran through the discussion, and I think in Martin Reese's talk this morning. Implicit in Martin's AI discussion is a claim, which sounds solid, a claim that the same technology that underlies interstellar communication is a technology that's going to underlie digital electronics and therefore artificial intelligence. The two are intertwined, they will come together, and therefore you expect AI takeover on a short time scale. I would like to see the claim of that necessary intertwining more critically examined, but it sort of sounds right. I will end these remarks just by saying there are other technical intertwinings that I think we assume are generalizable from our experience. Biotechnology and the transformation of the human species seems to be one of those because of the way bioinformatics underlies that. A more pessimistic comment is that the advance of computation brings with it opportunities for totalitarianism that are certainly not unique in human history, but seem to be powerful. There was a hopeful Apple computer commercial that made it look like the personal computer was going to be a driver for personal freedom. Let's hope that's right, but we have an alternative model now. We have a model in which the internet is surveilled, in which access to news is heavily restricted and filtered, in which the judiciaries aren't free, in which press is, in which the judiciary is not independent, in which press is not free. Authoritarian models to representative democracy are not confined to the 20th century. We have a powerful one that we face right now. And who knows what this means for SETI, but I think at the minimum it means that we should not assume that any entity we contact is anything like a culture that is familiar to us or one that we would wish to emulate. We simply don't know. I'll end with your question about the definition of life. Carol Cleland's work in this area came up yesterday. I want to emphasize that Carol's argument with the analogy to the Da Vinci Arundel Codex, where Da Vinci grapples with the idea of water, Carol's argument is that Da Vinci trying to define water in the year 1500 is hopeless. It's not his fault, but it's hopeless because there's no theory of molecules. Once you have a theory of molecules, you're not defining water anymore. You're giving a theoretical identity statement. Water is H2O, and that only makes sense in the context of a theory of molecules. You're not doing something like saying that a bachelor is an adult unmarried human male. It's a fundamentally different kind of exercise. If you believe, and this comes down to Anders' point, if you believe that life, that water is a natural kind, that it exists independently of human beings. The question is, and this is, I think, the central point in Carol's argument, is life a natural kind? If it is, then we need a theory of life and a theoretical identity statement, and a definition cannot solve that problem for us. If it is not, then we do the best we can.
Yes, thank you very much. Indeed, I agree here that we are at the stage of that description of life as Da Vinci described the water. So we put so many words and describing the processes and boundary conditions and how basically we can distinguish from life from no life, at least on Earth right here. And some processes, I think this description is still useful. We don't have definition, fine. But description is very useful in terms that we're looking for other forms of life somewhere else on other planets. And as much as we can describe life here in details of physical processes or chemical processes, I think that would be helpful for us to see whether that wave or something slimy moving structure on other planet, is it life or not? So how we actually distinguish that. And I think this is creates that background when we talk especially about life which is not Earth-like, because with the Earth-like we kind of can more or less describe what is life. But if it's not Earth-like life, or even if it's not chemistry-based life, then we have to go in terms of more basic physical processes, I think. And that brings us to the next question, which I would like to discuss with the panel and the audience, is that what would be the signatures of that life? In terms of processes, the life, we don't know actually which are the processes maintaining that life, but what would be the signatures we can search for and say for sure that, oh, that is a life signature. So a couple of years ago, Jeff Kuhn and I proposed to use the heat as a signature. I mean, similar ideas existed before with Dyson sphere, but it's on a small scale. If you look at Earth civilization on the temperature map from this near space, you can see our cities are heat islands. They are all above natural background by 10, 15 degrees Celsius. And that's constant heat present all over. So you can actually put the names of the cities on those dots. You know, it's very easy. And that doesn't matter what we do. We just, that through thermodynamics, we create that heat, we consume energy, and we have the waste heat. And whatever other life does, civilization or not, for instance, another example, if you drive in early spring into fields, you will see that some fields have grass and others not. And those which don't have grass, they have snow. And the fields which have grass, they don't have snow. And this is so contrasting, like it's about like 0 degrees in Celsius, let's say, at the level. So the life creates that heat which melts the snow. And so that is clearly biosignature. And so in this term, in these terms, I suggest our panel again go one round more and say, what are those say, universal signatures of life, even if we don't know what it consists of? Sara, you want to take on?
A couple things that were said, because I think there are a lot of interesting things which will roll into it. And one is on this point about whether life is a natural kind or not. I think that's a really fascinating question, but I think it goes back to a couple things that people have said so far, is that we really want to draw this like hard boundary around life and say this is life and this is not life. And I don't think that boundary is so black and white. So I think life is representative of kind of processes that we don't really understand yet. And it's a little bit like, I think an analogy that maybe is helpful is like thinking about gravitation and studying gravitation. That's something that we have a really good theory of now. If you want to understand gravity, you go and study very massive objects. So they're a representative of a gravitational system, but they're not the laws of gravitation writ large, right? Those are laws that describe nature and describe something fundamental about the structure of reality. I think what is happening with living systems that's really interesting is I think we don't really understand how information operates in the physical world. And if you want to understand how information works in physical reality, you go study a living system, because that's where those processes are most intense, right? That's where that physics is most representative. And so it's difficult to say it's a natural kind necessarily, because there are missing theories there. There are missing processes. We don't understand what that is. So I think that's actually, we can talk about definitions all day, but without that theory, we're really not going to understand what we're talking about. So I really love the analogy that Carol gave with thinking about water. So from that perspective, I think a lot of the definitions that we give for life, including the Darwinian one, are a little bit misleading, right? So just going back to the analogy of gravitation, when we're thinking about laws of gravitation, the greatest insights from that came from thinking very abstractly and came from thinking about a totally different physical phenomena. It came from thinking about the properties of light. I mean, who in their right mind would think that light was connected to gravity and would lead to the fundamental insights that the actual phenomena we see of an apple falling to Earth is because space-time is curved, right? So life, I think, is so much harder than that problem. But I think we have to think at the proper level of abstraction to really understand it. And so I think Penny made a nice point about patterns and the fact that life is this kind of set of patterns. And so one example that I'll give about how I think that this is maybe there's a lot of paths forward here, I think, if we start thinking at the proper level of abstraction to think about living systems. But we have chemistry we think about, right? So chemistry is the level of the scale of reality where life emerges, which should not necessarily be confused with the definition of life. So it's not a chemical phenomena, it's a kind of process. But what happens in chemistry is you get a particular pattern of transformations, and those patterns of transformations become living entities. So one thing that we've done in our own work in my group is actually try to look at biochemical networks, which are somehow capturing the patterns of how chemistry is transforming into other molecules. So you take molecules, how do they transform into others through reactions, and you can look at the entire pattern for a living system. You can do that for individuals, ecosystems, and the biosphere as a whole, and that structure looks incredibly regular. So the biosphere has very similar structure in terms of the patterns of how chemical reactions are wired together as an individual organism. And so there's something really fascinating to this about thinking about planetary scale life, which I think is this kind of interesting area emerging in origins of life literature, thinking more about life not as a localized transition, but a planetary scale transition, where you can't really use the Darwinian explanation to explain why the biosphere as a whole is so well organized. It has to be a different explanation. I think Darwinism and reproduction and cellularity and all these other things are derivative of some other kind of fundamental process. So I think that we need to understand those things. But there is something really interesting about thinking about looking for life once you start trying to understand the global organization of life, which we are obviously a part of. So none of this kind of definition precludes us as being representative of life, even as a society or a technological civilization or AI, so the long-term future, is that it gives you ways of thinking about how planets that have life might be organized or might have different kinds of patterns than planets that don't have life. So if we're thinking about these global organization of biochemistry, does that have an imprint in the global organization in the atmosphere? And it turns out that a lot of people do this kind of network science, like complex systems people love to just look at networks in different systems, and they had done some preliminary work in the early 2000s looking at the pattern of reactions in Earth's atmosphere compared to other atmospheres, and there seemed to be some differences. And so that's one area that we're working on that's actually trying to tweeze out whether you can actually not just look at the molecules present, but actually the patterns of transformations and how that physics is actually operating that would distinguish a living system.
Chemical paths of transformation.
Yeah. So I think this is it's a weird space to think in, right? And then the question is, what's structuring that, and how is it being structured, and then how is that leading to these higher scale phenomena? Right? So I think the hardest problem about life, which I mentioned in my introduction, is the hierarchy. It's not just that chemistry emerged life, but that there has been this cascade of increasing levels of complexity since then. And so one of the points that I thought that was brought up this morning that was interesting is that we think that as individual species, we're special because we're intelligent, and we're trying to explain that as a rare thing within all species on Earth. But we forget that we're part of a biosphere, and it's the biosphere as a whole that's evolving, including our technology emerging from us. And so we don't really know how likely that is. Maybe it's only one species per planet, but maybe that's a very deterministic process as part of how this complexity is unfolding. I think part of the problem is just we're always trying to draw boxes around these things, and life is this dynamic unfolding process, and it's really about the entire lineage. That is the life process. And so also this argument that we're going to create life on the lab and it's going to be different life. It's going to be a different chemistry. It's not going to be different life because we generate it. It's still part of our lineage. So I think there's a lot of hard problems here, but I think if they're clearly articulated, we can make a lot of progress. And so I think we need to think more in terms of these patterns and what the actual underlying processes are that are generating those kind of structures in order to really think about biosignatures. And the other point that I just wanted to make is that we're really fixated on this idea that we know what life is, and when we're going to look for it, we're going to recognize it. And I know there's been a lot of discussion here that we might not recognize it, and I think that's really true. And so one of the things that I think is a fun idea to play with is this idea that we might actually discover life on many worlds simultaneously and not a single world. And what I mean by that is not that there's been some intelligent civilization that's gone out and colonized, which would be super cool and could be a major discovery, but just that we have reasonably good theories for planetary formation and understanding the composition of different worlds that could be predictive in an ensemble sense or at a statistical level, but not necessarily of individual planets because they're so diverse and we have so little data that it's very difficult to predict a particular planet's composition. And so I think I think in order to really have confidence we detected life, we have to detect it in multiple places, and we have to do it statistically. And I think a challenge for the community is really to say, what is the confidence level? It's not going to be an aha moment that we're going to recognize life. We need a confidence interval. We need to know. We need to be like particle physicists and be like, it's the 5 sigma detection level. What is it for life? And so I think that we're just not, we are at the very beginnings of astrobiology as a serious science. It's a science of the future. I mean, like 100 years from now is going to be an incredible discipline to be in. But we need to set those standards now.
All right, thank you so much. Yeah. Laura?
Yeah, thank you for that. I'm so pleased you also think about life detection as a probabilistic thing. And that's exactly the sort of thing that keeps me up at night. But it's the thought that this is a vast number of possibilities that life could happen, and that we should consider exactly this kind of network of living organisms rather than just one individual form of life. That the fact that this is a finite number of possibilities. There is a finite number of possible networks that can be made. And so although it is vast and we should be contemplating it, there is hope. It is difficult but possible. And that does bring me into how I see the detection of life. And here there are 2 main approaches that I can easily summarize. And one of them is the kind of traditional popular one, which is very cool, which is to look for life as we know it. And I don't think we should be dismissing this. We do know of a handful of molecules on Earth that are crucial for habitability, and we should be looking for those in exoplanet atmospheres. But as we mentioned by many people here, they can all be vulnerable to false positives and false negatives. And even if you could explain every false positive scenario, and people have painstakingly done this, you still might just have false negatives, life that just doesn't look like you expect. Which is why, at least at the same time, we should be focusing on exactly this, that life as we don't know it. Even if we did find, oxygen and methane in the right combinations, and very exciting, that would be great, I'm not denying it. These molecules themselves, even in combination, when you take in consideration that we wouldn't just find them, we would find them within our own limitations, and that's limitations of our understanding of that planetary environment, the limitations in our own atmospheric models, the unavoidable noise from the observational data. These coupled do mean that, like Sarah said, that we're going to get a detection of life that is likely just going to be a probabilistic detection. We're going to detect it with a degree of certainty. And so we should be working towards not finding that smoking gun, which, yes, would be cool, but we should be working towards improving our odds. And improving our odds means considering the whole sophisticated biosphere and every molecule within it. And I'll take this concern to another level. Yes, to know exactly which molecules we should be considering for each type of living network on each type of planet is a really difficult question, and one I have no desire to answer in this exact panel, but should be left to a team of talented biochemists. But we can at least reasonably assume that it's not inevitable that life will exhibit the same biosignatures that we know on modern Earth. Even early life on Earth didn't exhibit those signatures. For the majority of the time there has been life on Earth, we haven't had oxygen as a biosignature. That's 2.4 billion years. And so we need to consider that the journey of life through chemical space needs to be carefully mapped and unraveled. And we can't do this by cherry-picking examples from biosignatures from modern Earth and life as we know it. Life as we know it is likely only one island in the vast archipelago of possibilities for life. And we need to have that in mind when we point our telescope, because I disagree with Sanders. I think the most likely thing is that we're going to look straight at an inhabited planet, and we will not have the tools to know it when we see it. And because those tools are not glamorous, they're not exciting. Actually knowing what all these molecules look like individually and molecules look like coupled in a network in a different environment, this is extremely difficult and painstaking. And I am working on figuring this out as fast as I can, but it's not straightforward to get spectra for thousands of molecules. You may think, just put them in a lab and measure them. And people have, and people should continue to do so, but lab experiments of molecular spectra are expensive, and they're often very dangerous, often not health and safety compliant at all. and really hard to extrapolate for different pressures and temperatures. And of course, you can do theoretical simulations like I did for my PhD, but that does take years of study and many graduate students. And it takes immense computer power, which is beyond...
Per molecule, we learned that, yeah?
Yeah, absolutely. And for most molecules, we just can't do this. But unless we do this, unless we have good spectra for as many molecules as are incorporated in this network, in this biosphere, then any detection or non-detection of a molecule or group of molecules is going to be open to misinterpretation, ambiguity, misassignment, degeneracies. I mean, you look at an atmospheric spectra, and it would be lovely to just say, yeah, I found HCN, and people do. And maybe you did find HCN. But are you sure you didn't find acetylene? Because those two molecules can look awfully similar in the right circumstances. And my program can tell you that hundreds of molecules in the right resolution or the wrong resolution and the wrong wavelength range can also be confused for things like acetylene and nitrogen cyanide. So when you are looking at these detections, you want to make these detections, particularly if you want to take it as a part of a larger network, you need to be worried about these things. And it's just a beginning. Even if you did know the exact spectra for every molecule that you could potentially care about that contributes to every biosignature in every biosphere, the spectra itself will be modified by the environment that it's in, the temperature and pressure of that atmosphere, the other molecules that are mixing and colliding with the molecule we want to detect. And so unless we do this, and we can measure this, we can calculate this, but currently we're missing the overwhelming majority of this information. So yes, we should be looking everywhere. We should be considering everything. We should continue to improve our instruments, reduce our noise, understand what we're looking for. But I still believe that the true bottleneck, or the biggest bottleneck in the detection for life, is our lack of concern and the poverty of our understanding of molecular spectrum. That will be our greatest bottleneck in the search for life, particularly the search for non-Earth-like life.
So thank you. This is still perspective on detection on chemical life, chemistry-based life, but not like ours, yeah?
Oh, yeah, if it's a phone call, we'll know it's live, yes.
So I think Anders can have a prospect like maybe on some intelligence kind of life. Like what would be like, it doesn't matter whether intelligence based on chemistry or machines. It's like what, from your point of view, would be interesting feature or process to detect?
So I think life and technology to some extent are part of a bigger continuum. And I think that might also be helpful for looking at generalized life signs. Post-biological life, for example, might have particular signs that might still be recognizable in an interesting way. Now, the cool part is, of course, that intelligent life is very much Maxwell's demon. We take a little bit of food and then we jot down things on a napkin, and before you know it, we arrange matter in a very clever way, and suddenly a laser shoots out. That's a very odd activity, really. And of course, we can say that that's because we're very intelligent technological beings, but to some extent, of course, even a primitive human making a simple trap is doing a very Maxwell demon thing, arranging the environment in a clever way, so relatively far into the future, a rabbit suddenly will stumble into that trap. Now, evolution is, of course, doing roughly the same thing, just that the amount of foresight is much less. Instead, it's doing a very broad search, testing out a lot of things, getting feedback, putting that information into the genome. But both of them are kind of example of getting a long-range order by an optimization process. Now, the interesting thing is most of the features are bounded, of course, by the laws of physics. There are certain things we can't do because of light speed limits, thermodynamic, gravitational collapse. And you might argue that these optimization processes would naturally tend towards these extreme limits. This is not really true for our biology. My bones, unfortunately, are not that strong compared to diamond. The terrestrial biology has not optimized for that strong bones. Photosynthesis is awesome, but it's still not maximally energy efficient, I think, compared to the quantum limits. The reason is, of course, that biology is trying to solve a lot of problems at the same time. A lot of the environment is because of other organisms that you're competing with, and evolution itself as a process is not really doing survival of the fittest, but survival of the most adequate. You're not really trying to optimize things perfectly, and that's good enough, and that produces a lot of interesting effects. Now, technology might be a bit different. Not always. Quite a lot of our technology also shows signs of economizing instead of getting to the boundary of the possible, which I think would indicate an interesting signature of something strongly optimizing. We tend to have something in the middle. But quite a lot of the technologies are moving towards the extreme physical limits. And I think there is a very useful way of thinking about that, and that is to try to compare the organic structures with technological structure. And this is an argument from a really old and forgotten paper by Eric Drexler, but it's a very good one, where he was thinking about, so my nanomachines, how are they different from biological replicators? And one of the most important things is, of course, in biology, we use diffusive transport to move things around. While in technology, we tend to have directed transport. We have a conveyor belt. We channel things in a particular direction. It's very effective, but you need to spend energy doing it. Diffusion just happens for free. This is, of course, why we care so much about solvents, because biology uses solvents to do things. But you can imagine a post-biological life that is using this form of channel transport, where solvents are relatively irrelevant. Another thing is that when you assemble things, in biology we do matching. We find something that acts as a template and something else that sticks onto that, and that's how we build things. That's kind of a secret, as we heard of yesterday, about our genetic code. Positional assembly, on the other hand, that's, again, what you find in a factory. You just put things in the right point, and then you add a screw, and then you link them together. Now, positional assembly is effective, but it's also very brittle. If things are slightly out of alignment, things doesn't work. As a Swede, I'm very well aware that this is what happens to most of my IKEA furniture, where I don't align it just right. We could imagine kind of organic furniture that where you just move things around and they snapped into place, and that might be a bit more like Lego. Now, the interesting part here is, of course, that this is a trade-off done because you get the evolvability. Similarly, we use a lot of topological structure in biology. It doesn't matter the shape really, but what's roughly connected to what can diffuse to what. While in technology, we make things that are very much, the metric matters a lot, which means precision needs to be high. We need to spend quite a lot of bits of information and entropy in making polished surfaces and smooth surfaces. And finally, of course, in biology, we use adaptive parts. String together neurons and we spontaneously form a neural network and start generating activity. Put a bunch of transistors together and they don't do that. Again, these inert parts have a lot of advantages. They are much easier to make and they're very easy to replace. It's hard to replace a neuron because it's grown together with everything else. And this, of course, gives us a bit of different style of biology and technology. And sometimes we can move between the parts of biology that are modular, but quite a lot of it isn't. There are parts of our technology that has these organic properties, but again, most of the practical technology isn't. So from a biosignature and kind of universal perspective, we might make use of this. We start looking at the thermodynamics and see, are things close to these limits? Are there examples where we can actually say that this seems to be using directional transport, where you don't have much of an, in either cases, you don't have an entropy cost for moving stuff around. But in one, you need to feed in energy. And that gives you different styles of energy and entropy and information flows, which I think we can actually use to better notice what kind of signatures there are. But it's noticeable that all of these systems, whether they're organic or technological, are kind of taking energy in, creating waste heat. That seems to be a rather fundamental thing. So the style of biology might be detectable by the kinds of waste heat. But I think we actually have a rather broad mutual sense. And this is why I'm not thinking life can get a pretty good definition, because even a little robot probe sitting in the Kuiper belt just waiting for a signal in standby mode, that's in my view life, but it's going to be terribly hard to detect compared to some squishy organism that needs a lot of sunlight. And as a small final point, just to contradict myself earlier, I think I'm allowed since I'm in the philosophy department. There is one interesting argument, which is a weak argument, but it's interesting, why our kind of life might be very common. And that is basically, if there are different kinds of life, there are different rates of them emerging from the right kind of primordial soup. The volumes of the different kinds of primordial soups, whether that is sulfuric acid or water or ammonia, are having vast differences. And on different planets, you also have different volumes that might have a right dryness, etc. You have also different time spans, etc. So you multiply together a bunch of different factors, which would suggest that you actually get a log normal or have a long tail distribution, which might mean that the most common form of chemistry is probably going to be dominating, that it's going to take up most of the pie chart. And we should, given our single data point, guess that we're in that one. So that's an argument for that actually most life isn't weird. This is a terribly weak argument based on observer selection, so one shouldn't trust it outside this room. But the coolest thing is, if we go out and find weird life, that's going to tell something about the structure of the distribution, and probably tells actually something about the rate constant and the volumes, etc. It's going to tell us much more about as yet unseen form of life. That's why I really think we should be looking hard for weird life.
Yes, excellent. Thank you. We need to accelerate a little bit. I'm sorry. We need to leave some time for the audience for opinions. Reese, you want to add something?
I'll try to be short. Hard for me. So searching for weird life, I agree, and that's, I think, what your question is. How do you search for weird life? I'm going to focus on Titan, because that's where I think we're going to find weird life first. And suggest 3 specific things we could search for.
Your new love object.
Pollution, Legos, and memory sticks. Okay, so let me unpack that a little bit. Pollution, David Catling gave a brilliant talk last year right here about thermodynamic disequilibrium, and is it or is it not a sign of life? And he was going to put a numerical analysis of that. On Titan, there is enormous thermodynamic disequilibrium. It's produced by sunlight. But what life would be doing is eating that thermodynamic disequilibrium. So in fact, I think you can make an argument, and Dave Grinspoon and others have made this, that the pollution of the environment by life on Titan will be the consumption of hydrogen. So that's the first thing we could actually do. We could go search for variations in hydrogen near the surface. There's no chemical expectation of such variations, but they are a plausible biological effect. It's the effect on its environment. We call it pollution. Life alters its environment. The second thing on my list was Legos. This has been discussed before. Life picks certain molecules and uses them. It doesn't use all the molecules. It's selective. It builds blocks. We call that Legos. Even life on Titan is probably following that same principle. It's building certain blocks. Chirality is a subset of this category. So we could search for that. The third category, I would argue, is Steve Benner's category, memory sticks. DNA is a memory stick. What does he mean? It's a stick in that the shape of the molecule is rigid and isn't impacted by the letters that are stuck on it, which is simple-minded but actually quite remarkable. If you think of a protein, the shape of the protein depends on what the letters that make it up. It's not a stick. It's a blob, and the shape changes. DNA is a stick. It's rigid. You change the letters, and the stick doesn't change. So it's a memory stick. Life needs a memory stick in order to encode information, and that memory stick can't change its shape. And Steve has clever ways of detecting memory sticks in waterborne systems. We need him to spend some time in liquid methane and think about how to detect memory sticks in liquid methane. Interestingly, Dragonfly, you might tell I'm biased toward the Dragonfly mission, can do the first 2. It will have a hydrogen detector, and it will hop from place to place. And if that hydrogen detector sees a variation in hydrogen, either temporal or spatial, that is very interesting, right? I will rise from my grave at the time and say, pay attention to that. Right? The second thing Dragonfly will have is a mass spectrometer that could, in principle, it's going to be difficult, but could, in principle, see the signatures of the LEGO, molecular selectivity and chirality. So it may be that after the Dragonfly mission, we are in a position to say there are clues to life. You know, that discussion at Breakthrough in 2018, was it, or 19 or 17, was prescient. Dragonfly can't search for the memory stick because Steve hasn't told us how to search for memory sticks in liquid methane, Steve. But that's what we'd like to do next. If we find hydrogen anomalies, if we find molecular selectivity, the clincher is to go find the genetic molecule on which Darwinian evolution is based. That's the memory stick. And then I think you've made the case that you found non-terran. You don't understand it yet. You can't define it. You don't know exactly how it works. But you've made a case that there's a Darwinian system operating on Titan, and that would be very cool. I would die a happy man.
Or rise from the grave.
Rise from the grave. That's the case.
As a happy zombie.
Wonderful. Thank you.
All right. I can be very fast here, actually, because there are 2 points that I think are really critical that we have not covered yet. One is this dichotomy between searching for preserved life, fossil life, or other non-living states. And then a lot of what the panel has said is really focusing on extant life. But as we are approaching our solar system particularly, and obviously we can't do this in the exoplanet realm at this point, but I've been searching for a way to connect these in terms of biosignatures. And to me, this is where the idea of patterns, and in fact, in terms of fossil preservation, it's patterns where the chemistry has been bleached away in most cases. Now, we do know that we have molecular fossils of various kinds here on Earth, but those are dependent on our prior knowledge of what Earth life's chemistry is. So when I think about this problem, plus the problem that Sara pointed out, and that is, this idea that we have a rigid box within which, if it doesn't meet this whole laundry list of criteria, it's not life. I think that's nonsense, because lifiness, as I think of it, lifiness occurs across a very broad spectrum. So in my mind, I have a sort of a n-dimensional phase space where you could put all of the ingredients that we know go up into making life here, and perhaps a few others that we could imagine for weird life that are not us. And within that, there is a very large amount of real estate. So we don't then have to be faced with the silly, mule problem and crystal growth and all these things that are humbugs that keep, torturing us when people are trying to stagger forward to a definition of life. So as long as whatever object or creature or whatever it is, or biosphere, fits within this n-dimensional lifiness box, to me it's life. Mm-hmm. And within that box, there is one corner of it that's devoted to preserved life, where you only have structure. Maybe you have structure at the microbial scale, maybe you have structure at the biotexture scale, maybe you have it on the whole planetary scale. To me, as a simple-minded geomicrobiologist, astrobiologist, structure is what catches my eye when I'm going into a new environment first. And then we can ask the questions about chemistry. So I think in many of our ways of thinking, we're focusing on chemistry because it is something that we can measure with payloads on missions, and that's very well, but I think we have to have this ingredient of structure because life creates structure at all different spatial and, in fact, temporal scales.
Mm-hmm. Exactly.
So I know that from some of my own work, we see patterns, physical patterns in this case. When we investigate further, we see chemical patterns. But when we actually do the genomics of who's there, it doesn't matter. The dramatis personae is irrelevant. So the pattern is insensitive to who the participants are, but not in terms of the functionality. And I think that you can extrapolate that much farther beyond our thinking about that on this planet, and extrapolate it to how do you see those salient patterns that are applied to radically different mechanisms to manifest that life. So to me, the chemistry is a very powerful mechanism for manifesting life, but it is not life itself. Mm-hmm. So I'm going to cut it off there because I really want to hear comments.
Thank you so much. Chris, briefly, you want to add something?
I'd like to build on some comments that Penny made yesterday in her talk on lessons from Viking. Let me first say that I think we should be proud of the Viking landers. People had asked that question for centuries, and as soon as we were barely able to try to address it, we went and did it. And in that respect, to me, it's similar to landing on the moon. It was outrageous that we tried to land on the moon with 1960s technology. It's ridiculous. But as soon as we could try to do it, we tried. And I think we should be very proud of all those missions. Having said that, of course, in retrospect, Viking seems premature, and whatever we do looking for life on Mars now is going to look premature 40 years from now. But I think if there is a lesson to be drawn from Viking, it's the importance of looking for life either explicitly or implicitly from the point of view of more than one definition. So Viking, you had the biology package, and those were all metabolic searches for life. And thank goodness we also had the GCMS, even though one can overinterpret, and perhaps we have overinterpreted the null result of the GCMS experiment. Having those two competing with each other and talking to each other, I think was very important. And I think that has lessons for what we do going forward. If we're going to fly through a plume on Enceladus, and that's a sample return mission, that's terrific, because we'll be able to do everything with that sample when we bring it back. If you're going to fly through the plume and all you're going to have is on board is a mass spectroscopy experiment, that begins to me to sound a little bit like Viking with just a metabolic package, just one experiment. And perhaps, and I don't want to put words in her mouth, but perhaps this is why Caroline was emphasizing landing, so you can do a lot more, as you could on Europa, say, or as you could on Mars. Final comment about Mars. I want to associate myself with Carol's remark yesterday, Carol Stoker's remark yesterday. I think it's time to actually look for life on Mars. There was a question from the floor, and I'm sorry I don't know the name of the person who asked it. There's a ticking clock now. I take that. I don't believe a decade timescale for humans on Mars. Somehow we're going to have humans always a decade away. But I believe that the situation is accelerated now, and we need to actually go after that question. And that means we have to look at planetary protection in the context of those kind of life search experiments, and we have to take that seriously. The Outer Space Treaty requires us to avoid the harmful contamination of other planets. Article 6 of the Constitution of the United States says that ratified treaties are the supreme law of the land. It's time to take that seriously and build it into our program. We have to do it for Europa and Enceladus anyway, and look for life on Mars.
Thank you so much. And that was pretty insightful, I think, discussion. And I have so many choices now.
Demand.
Okay, Lee.
We've killed it.
Okay. Oops.
I'd be happy to go into lunch.
Hello? Yeah. So I'd just like to thank the panel. I think I agree with almost everything that's said, but I would like to emphasize one overarching thing that we need to try and do, which is to generate a kind of a probabilistic approach that then leads a model that we may accept. So, I mean, obviously my bandwagon is let's look for unfeasible structures, complex patterns. Those patterns can manifest in imagery, in spectroscopy, and so on. And we need to agree the type of features that we're going to correlate, and then the experiments we look at. So everyone's got different experiments in mind. I can see all those, the human computers thinking about what experiment should we do. But I think Penny was closest to saying we need to zoom out and maybe think about structures. Mm-hmm. So my question or comment to the panel is, how do we unify all the concepts we've got to get? Because I was going to vigorously disagree with you, and then the point you said at the end, well, the reason I'm doing the thought experiment is I can draw a much bigger diagram and to look for new chemistry. Mm-hmm. It's like, oh, yeah, I understand. So it's a really nice set of comments, and I agree with them all. It's just I would emphasize the need for a probabilistic approach, one that we try and pull apart in the community, and then just think about, well, given a certain budget of experiments and funds and samples, can we then use that? Can we use this probabilistic approach again in listen as well as going to look for life? As Martin said today, thinking about life and biology and technosignatures, I think is a way forward. All right. And then cascading it down. And it could be chemically independent. Saying this from a chemist is a, I agree with you. It's not all about the chemistry, but it's
perfect. Thank you. We change sides. No. We change sides here.
Whoa,
we will switch from side to side.
Done.
Idea.
Testing 1, 2. Okay. Thanks for this interesting discussion. when you were all asked to define life, you came up with a lot of interesting ideas, and I agree with the points that we don't necessarily need and can't necessarily establish one definition of life. But there was one idea that I didn't really hear mentioned in that first round, although it was sort of hinted at in the second round, and that is the Lovelock and Margulis notion that life is inherently a planetary scale property. You were mostly talking about the properties of organisms and the effect of organisms on their environment. Now, is that useful? Well, the one inhabited world we know is a planet completely transformed by life, where you can look at life as not something that just sort of is an afterthought, but is a property of the planet. And so Margulis and Lovelock believe that that would be a property of all planets with life, that they would be flagrantly transformed. So I think that's worth considering as a hypothesis, and there's some implications of that. Lynn believed very strongly that there was no life on Mars, that you couldn't have life on a planet that wasn't obviously alive. And she might be wrong. It doesn't mean we shouldn't look for life on Mars, but it's a hypothesis we should entertain. And it's a testable hypothesis. Once we have 100 planets that we've really searched carefully, we'll know if that's true. So I just wanted to introduce that thought as one that might be worth having in the conversation.
All right, thank you. The cube here. Yeah.
All right, so really
You
amazing
hijacked
conversation. Huh?
You hijacked the cube, I saw that.
I did. Yeah. Thanks for the toss, Lee. So first of all, about Titan, I absolutely agree we should be looking in, around, or near the lakes. But one point that I wanted to make was that we don't necessarily need to look at things that are just soluble in methane and ethane, right? Because large molecules simply aren't. Steve did a very good job of talking about that. So what about the interface? What about essentially the benthic layer of these lakes, or the evaporite layer? And that's something that we're pursuing in the lab, and I'd like to hear your thoughts on that. And then second point, about Enceladus, and looking for sort of one single, or what Chris was talking about with using one instrument. You can still do multiple independent tests for life with a single instrument, right? As long as you're very clear in terms of your hypothesis and you're very open in terms of limitations of that particular instrument suite. And that's something that we should be thinking about as well.
All right, wonderful. Well, who is on the other side? Can you throw the cube to, here.
Ooh, I think we should.
Oh, you knew that was going to
We've got
happen.
almost no time left.
You knew that was going to happen.
No injuries, please.
Yeah.
Okay, so wanted to back up that remark because life terraforms. Okay, so Chris, you said that you look for life, it alters its environment, that it consumes a resource that's there. But if that's all that life did, life would not be a success. The whole history of life on Earth is one of making the Earth more fertile for life. Okay, life put oxygen in the atmosphere. Life created soil on the continents.
It was deadly, too.
And I think that our first definitive discovery of life in space will probably be made by astronomers who will see the spectrum of oxygen in extrasolar planetary atmospheres. And that will give it away. And that's
not necessarily a signature of life.
Well, if you find 20% oxygen in a planet's atmosphere, you have found life.
Well,
because oxygen is so reactive, it can never happen. Because look, excuse me, the universe is overwhelmingly composed of reducing elements. Okay, hydrogen is the most common. Okay, and by far. So you're not going to have free oxygen until you have life. We did not have free oxygen until we had life. There is no planet in our solar system that has free oxygen except the Earth. Okay? Now, if you find plentiful free oxygen in an extrasolar planet, you have found life. And after we've done this for a while and we find the characteristic frequency of planets with oxygen, and then we find a certain region of space that has 100 times the density of oxygenated planets as the average, you have found a civilization that is doing interstellar travel and terraforming planets and is spreading life. Okay, that's what you've found. So I think the way you will find life is by finding environments that have been altered in a way that is not compatible with non-life.
Yes, absolutely. So from this side, yes, please.
So in our discussions about the definitions of life, I think we want to be careful, rather than just talking about the individual and the planetary scale, we should be talking about living systems and signs of, is a system alive? Because most of the time when we're talking about definitions of life, when we're talking about an individual, well, that's a bit messy. It gets down to if you find a dead mule, it may not be alive, but it sure is a sign that there is a living system there. Now, when thinking about definitions of is a system alive, I think we also need to be very careful about the definition itself as opposed to the ramifications or mechanisms associated with that system. So a lot of people have been talking about evolution being incorporated into a definition of life. But if we as humans got to a point where we could make clones of ourselves that were guaranteed perfect information transmission, would we no longer be alive? We would stop evolving without any source of variation, but we would still be alive. And when we're looking for signs of life, I don't think we should be looking for evolution necessarily, because it could also be happening on very slow timescales, depending on how things are working. But what we are looking for is information being sustained for much longer periods of time than the substrate that the information is encoded in can last for. And when looking at it in those regards, the only way you can get that is by signs of life, or is by having life. And so evolution is a natural consequence of that, because in nature things are noisy. But I see that more as a consequence. And so when looking for these systems, we should be looking for the patterns. We should be looking for all of that lead to information being sustained.
All right, thank you. On that side first, here, yes. All right.
Side.
This side is more active, though, you know?
Yeah.
So, Chris brought up the issue of Darwinian definition of life, and I wanted to bring up the possibility that you could have panspermia, as often thought, by rocks carrying tardigrades to another planet. But there is also the possibility that intelligent life would put a 3D printer on a planet and produce synthetic life there. And I wanted to ask the panel if they have any thoughts of distinguishing life that did not follow from Darwinian but was synthetically produced on a planet versus life that was planted by a rock.
I'm sorry.
Wouldn't that synthetic life also be Darwinian once it's been produced?
Oh, well, once you let it evolve.
Nobody thinks that Darwin resulted in the origin of life. Darwin can't create life. It can just enhance it.
Multiply.
Right.
Well, it alters.
There's a puzzle. It can't be Darwin all the way down. Right?
Because we know there are turtles.
Right. Because if Darwinian processes are defining life, then by definition the things that come before life are not Darwinian.
Right.
So the transition from
let me rephrase. Can you distinguish initial conditions that lead to Darwinian, such that you will be able to tell between synthetic life and natural life?
I certainly can't. Maybe Steve Benner can.
Well, so that's a question today. If there is anyone on the
Maybe Steve can answer. Well, you have to answer.
It's over there. Yeah.
Yeah, look, what can I say without getting myself into trouble? The NASA definition of life is actually not a definition of life, it's a theory of life. It is a statement, a proposition, if you will, that we believe, if you will, that the properties that matter, the only way that matter can self-organize to give us properties that we value in life is by this process of random variation with errors, where the errors are themselves replicable. So if we, in a Star Trek world, encounter Q, a being that flits in and out of the continuum who's not chemical, right, we would have to revise that definition of life. Or if we had Arthur Hoyle's black cloud, which all of a sudden interceded between us and the sun and started criticizing us or apologizing for blocking off our sunlight, we would change that definition, but we don't do so now because we do not believe that a black cloud can exist or a Q can exist. Now, that's a theoretical statement, right? Nothing wrong with it. So the second problem about Darwinism is it's an inefficient way of producing properties that we value in life. Right? It's inefficient for a couple of reasons. First, because the chemistry, well, most chemical systems' behavior, shall I call it phenotype, that is the behavior that would confer fitness, that is behavior to small changes in structure. That is, the landscape is very rugged. If the landscape were smooth, Darwin I have no problem finding the global optimum, but the point is that, and this is an empirical statement, right? It's not a statement of theory, but what we observe is that chemistry is discontinuous, and the phenotype is a rugged function of changes in structure, and that means that Darwinism is very ineffective. The other reason why Darwinism is ineffective is because it requires the removal of bad experiments through the death of an organism, a baby, or even a reproduction age result, in which already has been invested a large amount of resources. So it's an unfortunate way of curing things. So what civilization does and what biotechnology does, is which is why it's not dangerous, is it does two things. First way, biotechnology can remove that. And of course, in China, for example, where we do in utero evaluation of a fetus and therefore abort it before too many resources are invested in that fetus, is an economic way of solving the problem that Darwin has, and which says you have to wait till the baby's, well, there is probably in utero selection in Darwinism as well, but never mind. The other thing that it does is it allows design. Darwinism does not let prospective change. That is, we cannot make a variation in Darwinism which we know in advance what its impact on future fitness is. And so what biotechnology and what intelligence does and what all the rest of this artificial intelligence. Now, by the way, artificial A-life is very nice because, right, what A-life does is it lets you ask, what can Darwinism conceivably do if it were not suffering under these very harsh constraints of chemistry? But this is John 1, right? Larry Krauss's favorite book. In the beginning was the Word, and the Word became flesh, right? Artificial life is the Word, and it's easy. The problem in Origins is making the word flesh, because the flesh, if I may say, the chemistry is suffering from all these constraints of molecular. And so when Sarah says, as she said a moment ago, which was rank heresy, that there is something bigger than Darwinism, which Darwinism is a derivative of, right? That is indeed creationism, right? That's, in fact, creationists are crazy, right? Because the creationists understand the problem. Creationists, for all that they, in terms of their solution, they invoke God, which I have a problem with. But
I think it just
at least
demands
they understand the problem. That it's very hard to get Darwinism started because the chemistry doesn't let you do it.
Sorry, you want to address that?
I'm not sure how to defend myself against that statement.
I'm with you.
Okay, you hijacked it.
I don't know. I don't know how you equate demanding explanation with creationism, but that's okay. I know. It's all right.
The point is that the problem is that getting Darwinism suffers.
Right, but that's why there must be some
actually get
explanation that goes
molecular
beyond
implementations
Darwinism.
of Darwinism is much easier in a computer than it is with actual real molecules.
Right,
so if I have
I
a
agree.
synthetic molecule life form, the question is, who did the synthesizing?
Yeah.
Well, an intelligent civilization, and then that is a biosignature. So the mule, by the way, we also hate the mule concept. Mule is not life, but it is alive, and it's a fundamental confusion of the property and whether the object has the property.
Even a dead mule.
Even that. A dead mule is a biosignature for sure. But yeah, so the point is that if you say synthetic life, you have to imply a synthesizer, and if it's not a synthesizer, you have to either A, change the definition of life, which is quite the theory of life. Right? You have to say, yes, there are ways that matter can organize itself to give properties that we value in life, which does not involve this process of random, non-prospective variation. Well, but Tesla is Mr. Tesla. The historical Tesla and Mr. Musk are both products of Darwinian evolution, if our theory is correct. Now, Elon might be Q for all I know. I mean, he certainly behaves like it, right? But the reason I don't think he is Q is because I don't, by my theory, don't think that Q exists. But maybe my theory is wrong.
So we have time only for a short comment, maybe.
Hello?
Paul's got it.
30 seconds.
Is it fair to say that artificial intelligence would not follow Darwinian processes because it would not be subject to the same kind of mistake correction? In other words, can AI evolve non-Darwinian ways because each step is actually an improvement? It doesn't make mistakes along the way.
Of course.
No longer Darwinian for the reasons that you just said. Right? You have learned to escape the constraints of Darwin.
Yeah, exactly.
Yeah, me too.
All right.
Well, the question becomes,
you want to
AI
have a
looks
short
back and say,
comment,
we were
or?
created.
That's what David said.
No. Okay, time out. Sorry.
I want to say something.
I'd like to thank everybody for this wonderful discussion. And I'd like to actually summarize in one sentence what we learned today. Do you want?
Oh, I want to hear that.
Yeah. So how do we detect non-terran life? So one sentence. Maybe that's long as Da Vinci sentence anyway. So what I heard here is that we look for patterns in time, in space, in chemistry, in heat, in structure. 5. So information, 6. I think it's a great summary, isn't it? Thank you.